Internation Panel on Climate Change. Frequently asked questions. These frequently asked questions have been extracted from the chapters of the underlying report and are compiled. Frequently asked questions. Is the natural removal of carbon from the atmosphere weakening? For decades, about half of the carbon dioxide, CO2, that human activities have emitted to the atmosphere has been taken up by natural carbon sinks in vegetation, soils, and oceans. These natural sinks of CO2 have thus roughly halved the rate at which atmospheric CO2 concentrations have increased, and therefore slowed down global warming. However, observations show that the processes underlying this uptake are beginning to respond to increasing CO2 in the atmosphere and climate change in a way that will weaken nature's capacity to take up CO2 in the future. Understanding of the magnitude of this change is essential for projecting how the climate system will respond to future emissions and emissions reduction efforts. Direct observations of CO2 concentrations in the atmosphere, which began in 1958, show that the atmosphere has only retained roughly half of the CO2 emitted by human activities, due to the combustion of fossil fuels and land use change such as deforestation. FAQ 5.1, Figure 1. Natural carbon cycle processes on land and in the oceans have taken up the remainder of these emissions. These land and ocean removals or sinks have grown largely in proportion to the increase in CO2 emissions, taking up 31%, land, and 23%, ocean, of the emissions in 2010 to 2019, respectively. FAQ 5.1, Figure 1. Therefore, the average proportion of yearly CO2 emissions staying in the atmosphere has remained roughly stable at 44% over the last 6 decades, despite continuously increasing CO2 emissions from human activities. On land, it is mainly the vegetation that captures CO2 from the atmosphere through plant photosynthesis, which ultimately accumulates both in vegetation and soils. As more CO2 accumulates in the atmosphere, plant carbon capture increases through the CO2 fertilization effect in regions where plant growth is not limited by, for instance, nutrient availability. Climate change affects the processes responsible for the uptake and release of CO2 on land in multiple ways. Land CO2 uptake is generally increased by longer growing seasons due to global warming in cold regions and by nitrogen deposition in nitrogen-limited regions. Respiration by plants and soil organisms, natural disturbances such as fires, and human activities such as deforestation all release CO2 back into the atmosphere. The combined effect of climate change on these processes is to weaken the future land sink. In particular, extreme temperatures and droughts as well as permafrost thaw, see FAQ 5.2, tend to reduce the land sink regionally. In the ocean, FAQ 5.1, Figure 1 atmospheric carbon dioxide, CO2, and natural carbon sinks. Top, global emissions of CO2 from human activities and the growth rate of CO2 in the atmosphere. Middle, the net land and ocean CO2 removal, natural sinks, and, bottom, the fraction of CO2 emitted by human activities remaining in atmosphere from 1960 to 2019. Lines are the 5 years running mean, error bars denote the uncertainty of the mean estimate. See Table 5.sm.6 for more information on the data underlying this figure. FAQ 5.1, is natural removal of carbon from the atmosphere weakening? No, natural carbon sinks have taken up a near constant fraction of our carbon dioxide, CO2, emissions over the last 6 decades. However, this fraction is expected to decline in the future if CO2 emissions continue to increase. Atmosphere natural sinks CO2 remaining in the atmosphere. Recent sea surface temperature trends hinder Antarctic stratospheric ozone recovery. 0. 1960-1980. Years. 2020-20. Billion tons of CO2 per year. Billion tons of CO2 per year. Proportion of emitted CO2 remaining in the atmosphere. Human caused emissions. Atmospheric growth rate. Ocean. Land. Frequently asked questions. FAQ 29. Several factors control how much CO2 is captured: the difference in CO2 partial pressure between the atmosphere and the surface ocean, wind speeds at the ocean surface, the chemical composition of seawater, that is, its buffering capacity, which affects how much CO2 can be taken up, and the use of CO2 in photosynthesis by seawater microalgae. The CO2-enriched surface ocean water is transported to the deep ocean in specific zones around the globe, such as the northern Atlantic and the Southern Ocean, effectively storing the CO2 away from the atmosphere for many decades to centuries. The combined effect of warmer surface ocean temperatures on these processes is to weaken the future ocean CO2 sink. The ocean carbon sink is better quantified than the land sink, thanks to direct ocean and atmospheric carbon observations. The land carbon sink is more challenging to monitor globally, because it varies widely, even regionally. There is currently no direct evidence that the natural sinks are slowing down, because observable changes in the fraction of human emissions stored on land or in oceans are small compared to year, and decadal variations of these sinks. Nevertheless, it is becoming more obvious that atmospheric and climate changes are affecting the processes controlling the land and ocean sinks. Since the land and ocean sinks respond to the rise in atmospheric CO2 and to human-induced global warming, the absolute amount of CO2 taken up by land and ocean will be affected by future CO2 emissions. This also implies that, if countries manage to strongly reduce global CO2 emissions, or even remove CO2 from the atmosphere, these sinks will take up less CO2 because of the reduced human perturbation of the carbon cycle. Under future high warming scenarios, it is expected that the global ocean and land sinks will stop growing in the second half of the century as climate change increasingly affects them. Thus, the total amount of CO2 emitted to the atmosphere and the responses of the natural CO2 sinks will both determine what efforts are required to limit global warming to a certain level. See FAQ 5.4, underscoring how important it is to understand the evolution of these natural CO2 sinks. FAQ 5.1, continued. Frequently asked questions. FAQ 30. Frequently asked questions. FAQ 5.2, can thawing permafrost substantially increase global warming? In the Arctic, large amounts of organic carbon are stored in permafrost, ground that remains frozen throughout the year. If significant areas of permafrost thaw as the climate warms, some of that carbon may be released into the atmosphere in the form of carbon dioxide or methane, resulting in additional warming. Projections from models of permafrost ecosystems suggest that future permafrost thaw will lead to some additional warming, enough to be important, but not enough to lead to a runaway warming situation, where permafrost thaw leads to a dramatic, self-reinforcing acceleration of global warming. The Arctic is the biggest climate-sensitive carbon pool on Earth, storing twice as much carbon in its frozen soils, or permafrost, than is currently stored in the atmosphere. As the Arctic region warms faster than anywhere else on Earth, there are concerns that this warming could release greenhouse gases to the atmosphere and therefore significantly amplify climate change. The carbon in the permafrost has built up over thousands of years, as dead plants have been buried and accumulated within layers of frozen soil, where the cold prevents the organic material from decomposing. As the Arctic warms and soils thaw, the organic matter in these soils begins to decompose rapidly and return to the atmosphere as either carbon dioxide or methane, which are both important greenhouse gases. Permafrost can also thaw abruptly in a given place, due to melting ice in the ground reshaping Arctic landscapes. Lakes growing and draining, and fires burning away insulating surface soil layers. Thawing of permafrost carbon has already been observed in the Arctic, and climate models project that much of the shallow permafrost, 3 m depth, throughout the Arctic would thaw under moderate to high amounts of global warming, 2 degrees C, 4 degrees C. While permafrost processes are complex, they are beginning to be included in models that represent the interactions between the climate and the carbon cycle. The projections from these permafrost carbon models show a wide range in the estimated strength of a carbon-climate vicious circle, from both carbon dioxide and methane, equivalent to 14 to 175 billion tons of carbon dioxide released per 1 degree Celsius of global warming. By comparison, in 2019, human activities have released about 40 billion tons of carbon dioxide into the atmosphere. This has two implications. First, the extra warming caused by permafrost thawing is strong enough that it must be considered when estimating the total amount of remaining emissions permitted to stabilize the climate at a given level of global warming, i.e., the remaining carbon budget, see FAQ 5.4. Second, the models do not identify any one amount of warming at which permafrost thaw becomes a tipping point or threshold in the climate system that would lead to a runaway global warming. However, models do project that emissions would continuously increase with warming, and that this trend could last for hundreds of years. Permafrost can also be found in other cold places, example mountain ranges, but those places contain much less carbon than in the Arctic. For instance, the Tibetan Plateau contains about 3% as much carbon as is stored in the Arctic. There is also concern about carbon frozen in shallow ocean sediments. These deposits are known as methane hydrates or clathrates, which are methane molecules locked within a cage of ice molecules. They formed as frozen soils that were flooded when sea levels rose after the last ice age. If these hydrates thaw, they may release methane that can bubble up to the surface. The total amount of carbon in permafrost associated methane hydrates is much less than the carbon in permafrost soils. Global warming takes millennia to penetrate into the sediments beneath the ocean, which is why these hydrates are still responding to the last deglaciation. As a result, only a small fraction of the existing hydrates could be destabilized during the coming century. Even when methane is released from hydrates, most of it is expected to be consumed and oxidized into carbon dioxide in the ocean before reaching the atmosphere. The most complete modeling of these processes to date suggests a release to the atmosphere at a rate of less than 2% of current human-induced methane emissions. Overall, thawing permafrost in the Arctic appears to be an important additional source of heat-trapping gases to the atmosphere, more so than undersea hydrates. Climate and carbon cycle models are beginning to consider permafrost processes. While these models disagree on the exact amount of the heat-trapping gases that will be released into the atmosphere, they agree that, the amount of such gases released from permafrost will increase with the amount of global warming, and, 2, the warming effect of thawing permafrost is significant enough to be considered in estimates of the remaining carbon budgets for limiting future warming. Frequently asked questions. FAQ 31. FAQ 5.2, Figure 1. The Arctic permafrost is a big pool of carbon that is sensitive to climate change. Left, quantity of carbon stored in the permafrost, to 3 m depth, NCSCDV2 dataset, and, right, area of permafrost vulnerable to abrupt thaw, circumpolar thermokarst landscapes data set. FAQ 5.2, can thawing permafrost substantially increase global temperatures? Carbon stored in the Arctic permafrost vulnerable to abrupt thaw. North Pole. Arctic Circle. North Pole. Arctic Circle. The thawing of frozen ground in the Arctic will release carbon that will amplify global warming, but this will not lead to runaway warming. 0 1000 2000 kilometers. 0 20 40 60 80 plus kg of organic carbon per m2. FAQ 5.2, continued. Frequently asked questions. FAQ 32. Frequently asked questions. FAQ 5.3, could climate change be reversed by removing carbon dioxide from the atmosphere? Deliberate removal of carbon dioxide, CO2, from the atmosphere could reverse, i.e., change the direction of some aspects of climate change. However, this will only happen if it results in a net reduction in the total amount of CO2 in the atmosphere, that is, if deliberate removals are larger than emissions. Some climate change trends, such as the increase in global surface temperature, would start to reverse within a few years. Other aspects of climate change would take decades, example permafrost thawing, or centuries. Example acidification of the deep ocean, to reverse, and some, such as sea level rise, would take centuries to millennia to change direction. The term negative carbon dioxide, CO2, emissions refers to the removal of CO2 from the atmosphere by deliberate human activities, in addition to removals that occur naturally, and is often used as synonymous with carbon dioxide removal. Negative CO2 emissions can compensate for the release of CO2 into the atmosphere by human activities. They could be achieved by strengthening natural CO2 sequestration processes on land, example by planting trees, or through agricultural practices that increase the carbon content of soils, and/or in the ocean, example by restoration of coastal ecosystems, or by removing CO2 directly from the atmosphere. If CO2 removals are greater than human-caused CO2 emissions globally, emissions are said to be net negative. It should be noted that CO2 removal technologies are unable, or not yet ready, to achieve the scale of removal that would be required to compensate for current levels of emissions, and most have undesired side effects. In the absence of deliberate CO2 removal, the CO2 concentration in the atmosphere, a measure of the amount of CO2 in the atmosphere, results from a balance between human-caused CO2 release and the removal of CO2 by natural processes on land and in the ocean. Natural carbon sinks, see FAQ 5.1. If CO2 release exceeds removal by carbon sinks, the CO2 concentration in the atmosphere would increase. FAQ 5.3, could climate change be reversed by removing CO2 from the atmosphere? Removing more carbon dioxide, CO2, from the atmosphere than is emitted into it could reverse some aspects of climate change, but some changes would continue in their current direction for decades to millennia. Atmospheric CO2, ppm. CO2 peak 600, 550, 500, 450, 400, 350, 300, 250, 1900, 2000, 2100, 2200, 2300. Yes, but years. Global surface temperature change, degree C. 2.5, 2.0. 1.5, 1.0, 0.5, 0.0, minus 0.5, 1900, 2000, 2100, 2200, 2300. Yes, but decades. Permafrost. Area change. Millions of km2. Ocean thermal. Expansion, m. 1. 0. Minus 1.
The stratospheric polar vortex is a large-scale, high-speed, cyclonically rotating wind system that forms in the stratosphere above the polar regions during winter, primarily due to the temperature contrast between the cold polar air and the warmer tropical stratosphere. It develops in the fall as the polar night begins and strengthens through winter, peaking in intensity during the coldest months. The vortex is centered on the pole and is maintained by the Coriolis force, which causes the air to rotate counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. The stratospheric polar vortex extends from the tropopause, around 12 to 15 kilometers altitude, up to the stratopause, about 50 kilometers, with the strongest winds typically found near the stratopause. It is most prominent in the winter months and weakens and eventually breaks down in spring, a process known as the final warming. In the northern hemisphere, the vortex typically persists until March or April, while in the southern hemisphere it can last an additional 1 to 2 months, often until November or December, due to a lack of large-scale planetary wave activity that would otherwise disrupt it. The vortex plays a crucial role in atmospheric dynamics and weather patterns. A strong, stable vortex confines cold polar air and isolates it from mid-latitude air, contributing to milder weather in mid-latitudes. Conversely, when the vortex weakens, distorts, or splits, often due to sudden stratospheric warmings, SSWs, it can lead to the displacement of cold air masses into mid-latitudes, resulting in extreme cold events such as the Beast from the East in Europe. These SSWs occur when planetary waves from the troposphere propagate upward into the stratosphere, disrupting the vortex and causing a rapid rise in stratospheric temperatures, sometimes by as much as 50 degrees Celsius, 411. The southern hemisphere's polar vortex is generally stronger, larger, and more persistent than its northern counterpart due to the absence of major land masses and mountain ranges that would generate disruptive planetary waves. This results in colder temperatures and lower ozone levels in the Antarctic stratosphere, contributing to the formation of the ozone hole. In contrast, the northern hemisphere vortex is more variable and susceptible to disruption by tropospheric weather systems. The vortex's behavior is monitored using various atmospheric parameters, such as potential vorticity, temperature at the 50 hours PA pressure surface, and zonal wind speeds at 10 hours PA, which are used to assess its strength and stability. 146 predictions of vortex behavior, particularly sudden stratospheric warmings, are now possible with advanced dynamical models, providing valuable insights for subseasonal weather forecasting. AI-generated answer. Please verify critical facts. October 26, 2025. The stratospheric polar vortex develops at latitudes above the subtropical jet stream. Horizontally, most polar vortices have a radius of less than 1,000 kilometers, 620 miles, since polar vortices exist from the stratosphere downward into the mid-troposphere, a variety of heights, pressure levels. The polar vortex extends from the tropopause, the dividing line between the stratosphere and troposphere, through the stratosphere and into the mesosphere above 50 kilometers. Low values of ozone and cold temperatures are associated with the air inside the vortex, northern hemisphere total column. March 5, 2021. The Arctic polar vortex is a band enclose a large pool of extremely cold air. There is an even stronger polar vortex in the southern hemisphere stratosphere in its winter. 2 weeks ago, we may see more polar vortex winters due to climate change. Sudden stratospheric warming gets everybody the most excited, Cohen said. This means that the air at the blowing from west to east around this cold air, this circulation of strong westerly winds in the stratosphere that forms every winter, is called the polar vortex. October 23, 2024. It isn't easy to comprehend, but the stratospheric polar vortex SPV can suddenly and significantly impact winter weather down here on the Earth's surface. 2 weeks ago, both Butler and Lopez Lang said having accurate forecasts for polar vortex events can help make 7 to 10 day forecasts better, which can be beneficial for decision making. Even though the stratospheric polar vortex is miles above us, it's sometimes connected to our weather via invisible puppet strings we describe with atmospheric dynamics and thermodynamics, Lopez Lang said. The polar vortex is the region of high atmospheric vorticity that forms with the establishment of the winter stratospheric polar jet. Figure 1. The polar jet begins just above the tropopause in both the northern and southern hemispheres, reaching maximum wind speeds near the stratopause, 50 kilometers. March 6, 2025. This is expected because strong polar vortex winds act as a barrier between cold Arctic air and warmer mid-latitude air. As the polar vortex becomes disrupted, the stratosphere will warm quickly and intensely, bold pink line, hence the name sudden stratospheric warming. October 21st, 2020, thus the cold stratospheric air, known as the polar night jet stream. The polar night jet and the cold air which it encircles collectively form the cyclonic stratospheric polar vortex, instead of circulating the South Pole. The polar vortex becomes elongated and winds weaken. The weakening winds result in considerable stratospheric warming over Antarctica. The maps above show air temperatures in the middle stratosphere at about 30 kilometers altitude or 10 hectopascals of 2 weeks ago. That part of the atmosphere is usually bitterly cold, with strong west to east winds whipping around the North Pole like a racetrack. That spinning ring of winds is called the polar vortex. December 20th, 2023. Earth's west to east rotation, and they are strong enough to act as a barrier between the mid-latitude and polar air, reinforcing the cold stratospheric air within the vortex. The vortex exists every winter, but it is far from constant. It strengthens, weakens, stretches, distorts, and occasionally fractures. These shifts do not stay in the stratosphere. They cascade downward, altering the jet stream and the weather. January 15th, 2025, the stratospheric polar vortex forms in fall when there is no solar heating in polar regions, and large-scale meridional temperature gradients strengthens during winter and then breaks down, and high-latitude winds become weak easterlies. The stratosphere is the layer of the atmosphere extending from approximately 6 miles to approximately 31 miles above the surface. The stratospheric polar vortex, we bet you've heard of the polar vortex, resides in this area and can significantly influence weather in the mid-latitudes. Located near the poles, hence polar, this spinning cone of low pressure or vortex is always there in the colder months. But it's high up in the stratosphere, that layer of the atmosphere above which most of our weather occurs. As the waves move upward into the stratosphere, they have two effects. First, they will often push the polar vortex away from the North Pole, bringing warmer mid-latitude air poleward. And second, they produce a downward motion field that also warms the polar region. Due to the opposite seasons in the northern and southern hemispheres, it is very